My name is Kevin de Vriendt, and I'm a PhD student at the Spanish National Research Institute, CSIC, in Barcelona. And my two main supervisors are Maria Pool and Marco Dens. And my main PhD thesis is looking at mixing and reactions that occur at the salt-freshwater interface. So since I've just started my PhD, the first thing that we're doing is just taking a look at a numerical study on how mixing and calcite dissolution occurs in a heterogeneous environment. So, of course, we need to generate a synthetic media, and to do this we generate log-normal multi-Gaussian random permeability fields. And in order to generate connected and disconnected fields, we use a method by Zinn and Harvey to transform our data that generate high conductivity paths and low conductivity paths. And so, using these permeability fields, we then generate a chemical reaction problem where we use a very simple method by De Simoni, who decouples the solute transport problem and the chemical speciation problem. So scalar dissipation gives us an idea of how concentration gradients are created and how they're attenuated by dispersion. Coupling this with the speciation term, here we can implement what's happening with the reaction of fast calcite dissolution. So obviously there are a few simplifications we have to make for this to generalize the problem. We assume it's steady state, we assume there's no change in the flow field, and that means no changes in porosity or permeability. So we say that the compositions of the two different waters are different, and when they react, this will result in a reaction. And the problem alone is quite interesting because in the homogeneous case, you already have two hotspots that are generated. Other studies have already talked about this, but we have one hotspot that's occurring due to dispersive mass fluxes, due to the convective cell that's occurring, and then another one that's mainly due to the speciation term, due to the undersaturation conditions that are created when the two waters first meet. Another thing that we wanted to look at a little bit in this problem is how flow deformation can tell us something about mixing. So we look at the rate of strain. So this measures somehow the local stretching deformation that's occurring between these heterogeneous fields. So this can directly tell us something about how mixing and reaction actually occurs in our system. And obviously, to evaluate the differences during our Monte Carlo simulations, we have to have a few diagnostics. So to discern the global behavior, what we do is, for the width of the plume, we look at the second-centered moment of the mixing ratio. And we see that in connected fields, we have a much larger increase in the mixing width. And this naturally results in larger global reaction rates. And then if we look into the more local reaction rates and spatial sampling within our fields, we see that as we increase the variance, the reaction rates increase drastically. So not only can this tell us something about connection, disconnection, but if we generalize the problem to perhaps we have a fraction media which is highly permeable or a fraction media that's not permeable, or even if we have a barrier in our system, how do reactions occur in these specific fields, especially in a saltwater intrusion one where the flow topology and the flow field in general is very unique. And without getting into much more details, what I'll be concentrating on further into my PhD will be looking at first tank experiments and looking at reactions that occur between the two using different traces that emit a photon. And then further moving on, we might use field data to motivate numerical models for very practical applications such as nitrate transport and phosphate, the fate of phosphate and other nutrients in systems, and how these actually react within the domain of saltwater intrusion. So if you want more information, feel free to contact me via email or through the Enigma ITN website. Thank you very much.